Hello, everyone. I'm Leighton Gray. I'm an engineering team lead for Bradken, and today I'd like to present a case study on how we eliminated chute plugging while enhancing wear liner life. So, to set the stage a bit, let me walk you through a roundup mine site. Starting at the top, ore is dug up from the ground and brought over to the primary crusher via trucks. Here, the primary crusher crushes the ore into a smaller size, which then travels to an apron feeder towards this coarse ore stockpile. From there, it moves again to a secondary crusher, where it gets crushed into a smaller size again, and off towards the screen bins. From the screen bins, it gets separated with larger ore, which re-enters the cycle to get crushed again, and then come back, and then the smaller sizes get filtered through a screen towards the ball mills, which continue through the circuit. For this presentation, we'll be focusing on the screen bins. To give a bit more context on how this component works, material is dropped onto the top of the screen deck on the right side, and this screen vibrates, which causes the smaller material to fall through apertures into an undersized chute, while the oversized material gets pushed along to get recrushed and resent back to here. The problem at this site is that they had frequent pluggings for the screen undersized chute. They are currently screening 3,200 metric tons per hour, but they have plans to go up to 4,400 metric tons per hour. So, digging into the problem a bit more of frequent plugging, they found that the fine material would build up and cause plugging, with this problem being worse in winter. They also found the first thing they tried to do is to try different wear liners, something with a lower coefficient of friction, such as Tyvar 88, but they ended up finding out that this only lasted a few days. They were currently using AR500 and chromium carbide overlay plates, which they plug weld into the chute wall itself. This caused a lot of pain to maintain, since they would have to gouge out the liners, while also causing areas that could promote ore buildup with all the plug holes. They would also have to enter a confined space whenever they needed to change out these liners. So they tried a couple of ways to mitigate this issue. With limited control on the ore size, they tried blanking a couple of screens, so they wouldn't have as much material go into the undersize right away. They tried adding in heaters to prevent the ore from freezing up in the winter, and they also installed air cannons, which could blast the material before it built up too much. But overall, they found this wasn't effective enough to completely solve their issue, which still caused unnecessary downtime, confined space risks, and a hazard of material avalanching. So we wanted to get into the root cause of this problem, which is frequent unplanned downtime. We looked at a couple of issues, such as maybe the liners being installed inconsistently with the weld, the cold temperature promoting buildup, but overall, we wanted to focus on two parts of this, which is the equipment with the wall angles being too shallow, and then the materials of the wear liners themselves. So we tackled this in three ways. Firstly, by changing the geometry of the chute. Secondly, changing the wear liner package. And then thirdly, designing with maintenance in mind. So first of all, with changing the chute geometry, we changed the wall angles to promote better flow by increasing the open area. On the right side here, you can see the gray structure, which is the original chute, compared to the proposed chute with the circled highlighted red area there, and how much more room is there. So if material does fall off, it has enough room to still make it through the chute. Secondly, we move to curved corners. As two walls come together and create a corner, it creates a dead zone that material can build up. So going to curved corners, we ended up eliminating that issue. Thirdly, we also changed the wall angles of the chute. With steeper wall angles, it allows for less material to build up before it tries to fall off and go through the chute. So we can validate this a couple of ways. Some such is by using discrete element modeling with a couple of parameters here, which shows us a result here with the existing chute on the left and then the proposed chute on the right. So you can see the left chute ends up filling up by a big avalanche, while the proposed chute, the material does build up slightly, but has enough room to fall and go through the chute still. This design was validated by a third party, Janicki and Johansson, another expert at the field of bulk solids. Secondly, we changed the wear liner package. So we went with ceramic liners in heavy wear areas since they have a low coefficient of friction and don't allow a lot of material to build up. We ended up going for chromium carbide overlay plates for the curved corners to match that surface structure with a polished surface finish, which is even smoother than regular. We also improved the wear liner package, replacing the AR with more durable liners, such as the ceramic and the CCO in its entirety. And then lastly, we moved to studded liners, which eliminates the plug weld holes that promote flow, while also facilitating easier change-up times. Lastly, we designed for fast changeouts. The entirety of the chute gets lifted out in 2 parts, with the goal of having another pre-lined chute ready to get installed right away. This means that you don't have to spend time changing out the liner package during your shutdown. You would just have another chute lined and ready to get lifted in. It also makes it even quicker to reline since it is studded as opposed to a plug welded on. It also eliminates any confined space risks of having someone enter the chute to reline the total structure. The site itself was going from 6 days to an expected 1 day of changeout time once they refined their install process. To summarize the changes, we went from consistent chute blockages causing hours of downtime to eliminating plugging through geometry changes. It went from frequent liner wear, creating costly spot repairs, to liner life matching their maintenance schedules, and an improved safety by reducing the confined space for all maintenance. And then lastly, reduce the reline time in total with studded liners and removable design. The next steps from here would be condition monitoring. So we could do smart liner sensors, which is basically an active wear monitoring sensor inside the liners that will tell how much wear liner life is left. And then gather feedback from the maintenance crew and see which sections wear more in case there's any more improvement we can do to the wear liner package.